Welcome back, everybody. In this problem, we'll be taking a look at the force upon one current-carrying wire due to a traveling current in a different wire. Because traveling currents produce magnetic fields, that field will be the mediating factor here. So the approach will be to find the magnetic field produced by one of the wires and then use that to find the force upon the other wire. Along the way, we'll be dealing with vectors, so we'll have to be careful not only with their magnitudes, but with their directions as well. Let's go ahead and take a look at the problem statement. As usual, let's formulate a plan on how to attack the problem. We're asked to find the force upon this loop due to this wire. And so again, the mediating factor here is the magnetic field, so what we're going to do first is have to find the magnetic field due to this wire, and then once we know the magnetic field in this region, we can find out the force by crossing that with the magnetic field. So let me go ahead and write down the plan here. The first step will be to find the magnetic field due to the top wire. So we'll use current I1 to find the magnetic field. And because it's a long, straight, more or less infinite wire with a constant current, the magnetic field for this has been tabulated. You probably may have it memorized, but we're going to go ahead and rederive it using Ampere's law, just as practice. So we're going to use Ampere's law to determine the magnetic field due to that current. Now once we know the magnetic field in this region, we can cross it with the current to find the force upon that wire. So the next step will be to use the field to find the force, and if you recall, the force upon a current in a magnetic field, the force per length is equal to the current crossed with the magnetic field. So we're going to use B to find the force. And then we can find the force in each one of these four segments, and adding them all up, we'll find the net force, which is what we're being asked for. So the last step will just be to add up all the forces. So starting this off, let's first find out what the magnetic field is produced by the top current using Ampere's law. I'm going to have you guys do this on your own, actually, and we'll come back and take a look. So as always, start off by drawing an Amperian loop around it, integrate the magnetic field around it, and then set that equal to the current and solve the magnetic field. We'll come back and take a look in a moment. To utilize Ampere's law, the first thing we have to determine is what does our Amperian loop look like. While Ampere's law is actually true for any Amperian loop, it's only useful when you have a loop which respects the symmetry of the problem and for which the magnetic field is either perpendicular or parallel at all points in the loop. Let's first get an idea which direction the magnetic field points using the right-hand rule. So for this particular wire, the magnetic field will always point circumferentially around it. Using the right-hand rule, you point your thumb in the direction of the current and your fingers will curl in the direction of the field. So above the wire, it looks like the field is going to come out of the screen. In front of the wire, the field will come down, and then below the wire, it will come back into the screen, etc. So we want to draw a loop that just kind of respects the symmetry. So the loop is very simple. You just want to make it a circle around the wire. So let me go ahead and draw that. I'll draw the wire. I'll just reproduce the wire from there. And it carries current I1. Okay, so this is your Amperian loop, and again, the magnetic field just kind of points circumferentially around it, so it kind of looks like this, using the right-hand rule. Now that we have our loop, we can write down the statement of Ampere's law, and we'll see that the integration becomes trivial, which is why Ampere's law is useful. So the statement of Ampere's law is that the magnetic field integrated around the loop equals the current times a constant, the current piercing the loop, which in this case is I1. Now in this case, the magnetic field at any given point is perpendicular to the direction of the loop itself. So at all points, the tangent to the loop and the magnetic field are parallel. So these vectors are parallel. So the dot product of them equals the product of the magnitudes. So that's why that's useful to draw a loop like that. So you don't have to worry about any of the directions between them because they're all parallel. And then also the magnetic field is constant everywhere. It's the same everywhere on the loop because we're looking at points the same distance from the wire. So the magnetic field should be the same there. So everywhere on the loop, B is the same. That means it's constant. We can pull it out of the integral. And what we're left with is just an integral of a path, of a differential path, which is just the total path length. The path length around the circumference is just equal to the circumference, of course, which is 2 pi r. So if we're looking at a distance r away, sorry, it should be I1. Okay, I1. So finally, solving for the magnetic field, you get that the magnetic field equals mu naught I1 divided by 2 pi times the radial distance from where the wire is to where you're measuring the field. So this tells us that the magnetic field, well, it would be constant. All these are constants except it's inversely proportional to how far you are away from the wire, which indicates that as you get farther away from the wire, the field diminishes in its magnitude. And as we noted earlier, it's pointing into the screen here. So we can just write the field a bunch of x's to indicate that it's in the screen. But what I'm going to do is I'm going to draw those x's with diminishing size just to indicate that the field is getting smaller as you get further away from the wire. This is kind of a graphical way to illustrate that. Okay, so the field is always pointing in this direction below the wire, but it decreases in magnitude as you go further away from the wire. Okay, so we have the field. We know the exact mathematical form of the field itself. We also know which direction it points. Now using that, we can find the force upon that loop. So the next step, which is step 2, is to find the force per unit length on each part of the wire. Right, so the force per unit length will equal the current crossed with the field, which we just found. And before we do that, we want to get an idea of the directions of the forces. Because the wire is going in all these different directions, you can imagine that the force direction will be different in all pieces of the wire. So first get an idea which direction the force points on in each segment of the wire. You can do that on your own, find that direction using the fact that you know which way the current goes and using the fact that you know which way the field points. And also, if you get the directions, I'd like you to maybe go a little further and try to determine the relative magnitudes, maybe just a qualitative assessment of which parts have a stronger force on them because this quantity is bigger. So if you think you know that, maybe draw the vectors on that particular part of the wire a little longer to reflect that they have bigger magnitude. So go ahead and take a minute now, find the directions, maybe the relative magnitudes, and we'll come back and take a look. So looking at the forces one by one, we'll start with the top segment. I'm just going to reproduce the picture over here so it's not cluttered. On the top segment, we have a current pointing to the right, and the field is pointing into the board, which gives us a force that points upward. On the right-hand segment, we have a current that points downward, and the field is pointing into the board again, which gives us a current pointing to the right. But notice that the field itself is diminishing as you get further away from the wire, which indicates that the force will also diminish as you get further away from the wire. So to indicate that, I'm just going to draw a few vectors that get smaller. Okay. On the top, however, they're all the same because the wire is the same distance from the first wire, so the field value is the same everywhere there. So you have the same force. Now on the bottom, we have a similar thing to on the top, except now that we're further away from the top wire, the field is diminished, so the force has to be less, and it points down. And then on the left-hand side, we're going to have something similar to the right-hand side, except in the opposite direction. You'll notice from this picture that all the forces on the right-hand side will cancel with all the forces on the left-hand side, giving a net force of 0. The force on the bottom and the top will not cancel because the top has a larger magnitude of the force. So the net force will point in the positive direction. So we do need to find those magnitudes individually, so let's go ahead and write that down. The force in the top segment is, so the magnitude of the force is the magnitude of the current crossed with the magnetic field. And of course the magnitude of a cross product is the product of the magnitudes of the vectors times the sine of the angle between them. For the magnetic field, we have it equals mu naught times the current divided by 2 pi. And then r in this case is the distance that we are away from the first wire. And the top segment everywhere is a distance of a away, so we're going to put a there. The sine of 90 is just 1. What I forgot to write over here is that this should be force divided by length, so force per length. So we should have force per length gives this quantity right here, and then if we want to find the total force in that segment, we just multiply this quantity by the total length, which is L. So the force in the top segment is the following quantity. Right, and you can find the force in the bottom on your own. It's a very similar type thing. Go ahead and do that now. Find the force in the bottom, and then subtracting those, you can find the net force, and then try to write it in unit vector notation as the problem asks. Take a minute to do that now. I'll come back and take a look. And the net force we get is just the difference between the force pointing, the force in the top segment and the force in the bottom segment. And if you plug in the numbers, you should get 3.2 millinewtons. And so the vector representing this force, because it points in the positive y direction, is 3.2 j, and the units are millinewtons. And so that's the answer. Let's take a look at the summary. In this problem, we were asked to find the force of one current carrying wire upon another. We first determined the magnetic field of the first wire using Ampere's law. Then we found the directions and magnitudes of the forces upon the wire segments in the loop using the fact that the force per length is a cross product of the current in the field and using the right-hand rule. Finally, we sum the force vectors to get the net force vector upon the loop. So that's it for this problem. As always, if you have comments or questions, please leave them on the link attached to the video, and we'll see you next time.